Welcome to lesson 5.6 Optimization and Deployment. Overview. You've built a chat model with real personality, multi-turn capability, and advanced features like function calling and retrieval. Now comes the part that separates a research experiment from something you can actually ship, making it production ready. This lesson covers inference optimization, memory reduction, deployment strategies, and monitoring, everything you need to take your model from a Jupyter notebook to a running service. Budget about 60 minutes and expect to come away with working deployment code you can use immediately. Learning objectives. By the end of this lesson, you'll know how to optimize inference speed and latency, reduce memory usage and deployment costs, choose the right quantization strategy for your hardware, deploy your chat model as a real web service, monitor it in production, and handle the edge cases and failures that will absolutely happen once real users start poking at it. Optimization strategy overview. Before touching a single line of optimization code, understand the constraint you're working inside. There's a classic engineering triangle here: fast, cheap, and accurate, and you only get to pick two. This isn't pessimism, it's physics. Aggressive quantization gives you fast and cheap, but you trade away some accuracy. A large unquantized model on high-end GPUs gives you fast and accurate, but the cost is real. Running full precision on a small GPU gives you cheap and accurate, but you'll be waiting. Every optimization decision in this lesson is really a decision about which corner of that triangle matters most for your specific use case. Know your answer before you start tuning. Inference speed optimization. The first code block sets up a proper inference benchmark. It loads your fine-tuned model with 4-bit quantization, then runs a warm-up pass before timing anything. That warm-up is important because the first inference call always includes CUDA kernel compilation overhead that would skew your numbers. The actual benchmark loop runs multiple passes and averages the results, giving you three numbers to watch: average inference time in seconds, tokens per second, and latency in milliseconds. On a Tesla P40, running a Llama 3.2-3B model in 4-bit, expect roughly 20 to 30 tokens per second and a latency of 8 to 12 seconds for a 256 token response. Run this before any other optimization so you have a real baseline to measure against. Otherwise, you're just guessing whether your changes helped. Flash attention is a memory-efficient attention algorithm that rewrites the attention computation to avoid materializing the full attention matrix in GPU memory. The result is a 2 to 3x speed improvement on supported hardware. The code here shows how you'd enable it. Setting use underscore flash underscore attention underscore 2 to true when loading the model. There's one hard constraint though. Flash attention requires Linux. It is not available on Windows, full stop. The CUDA kernel it depends on won't compile on Windows. Since you're running Windows 10 with your P40S, skip this optimization entirely. It's not a workaround situation. Just move on to the techniques that will actually work on your setup. When multiple users hit your model simultaneously, processing each request one at a time is wasteful. The GPU has parallel compute capacity sitting idle between requests. Batched inference fixes that. This code configures a transformers pipeline with device equals sign 0 to target your first GPU and batch underscore size equals sign 4, meaning 4 prompts get processed in a single forward pass. The requests list feeds multiple prompts at once, and the pipeline handles the batching automatically. For a single user scenario, the improvement is marginal, but for applications handling concurrent traffic, batching delivers 2 to 4x throughput improvement. You're serving more users with the same hardware. This one is straightforward but surprisingly high impact. The naive approach sets max underscore new underscore tokens to 2048, the full context window. which means the model keeps generating until it hits that ceiling or produces an end-of-sequence token. For chat responses, that ceiling is almost never reached. Most replies are under 256 tokens. The optimized version sets max_new_tokens to 256 and explicitly passes the EOS_token_ID, so the model stops the moment it naturally finishes a thought rather than run. The speed improvement is 4 to 8x for typical chat responses, not because the model got faster, but because it stopped doing work it never needed to do in the first place. KV caching stores the key and value tensors computed during attention for each token, so when the model generates the next token, it doesn't recompute attention over the entire sequence from scratch. Without caching, generation time scales quadratically with sequence length. With caching, each new token only attends to the cached past. The code here passes use_cache true to model.generate, which is actually Onslaught's default, so you're already getting this benefit. The improvement is roughly 30% faster generation on longer sequences. It's worth knowing it's there and confirming it's enabled, especially if you're working with a custom generation loop that might accidentally disable it. Temperature controls how the model samples from its probability distribution over the vocabulary. At temperature 0.8, the distribution stays relatively spread out. More tokens are in play, which means more diverse outputs, but also more computation spent evaluating candidates. Dropping to 0.3 sharpens the distribution, narrowing the effective candidate set and speeding things up slightly. Setting do_sample false switches to greedy decoding entirely. Always pick the highest probability token. No, that's the fastest option, giving you 10 to 20% speed improvement, but outputs become deterministic and noticeably less varied. For a customer-facing chat assistant, temperature 0.3 to 0.5 is usually the sweet spot. Fast enough, still feels natural. Cost optimization. Here's the comparison that should drive your deployment format decision. A LoRa adapter loaded on top of a 4-bit base uses about 6 GB of VRAM and runs at 20 to 30 tokens per second. That's what you've been working with during development. A merged 4-bit model where the LoRa weights are baked into the base and the whole thing is quantized drops to 3 GB of VRAM and actually runs faster at 25 to 35 tokens per second because there's no adapter overhead at inference time. Merged 16-bit jumps to 7 GB but gains another 5 to 10 tokens per second. Full 32-bit hits 14 GB and tops out at 35 to 45 tokens per second. For deployment on your P40S, merged 4-bit is the clear winner. Smallest footprint, fastest load time, good inference speed, and no LoRa loading complexity. That's the format to target. This code performs the merge. It loads your LoRa adapted model the usual way with load_in_4-bit =true, then calls save_prep9_merged on both the model and tokenizer, pointing to an output directory and specifying merged_4-bit. What happens under the hood? The LoRa adapter weights get mathematically merged into the base model's weight matrices, and the result is quantized to 4-bit and written to disk as a standard Hugging Face model directory. The output will be 2 to 3 GB on disk and loads exactly like any other model. No Onslaught dependency required at inference time. No adapter configuration to manage. This is the artifact you'll actually deploy. Deployment options. FLMAN options. When Seri techniques quickly. The Flask server is the simplest production option. A single Python file that loads your merged model once at startup and exposes 2 endpoints. The /chat endpoint receives a JSON payload containing a messages array plus optional max_tokens and temperature parameters, runs inference, and returns the assistant's reply along with a token count. The /health endpoint returns a simple status check. This matters more than it sounds because load balancers and container orchestrators use health checks to decide whether to route traffic to your instance. Notice the model loads once at module level, not per request. Loading a 3 GB model on every request would make your API unusable. When you start this server and see model loaded, server starting in the terminal, the model is in memory and the API is ready. Run this command from your project root to start the Flask API server. The script path assumes your deployment code lives in a deployment/subdirectory. Adjust the path if your structure differs. Watch the terminal output. You'll see the model loading progress first, then Flask's startup message showing the address and port it's bound to, typically 127.0.0.1 If you see a CUDA error here, it almost always means another process is already holding your GPU memory. Check Task Manager and kill any lingering Python processes before retrying. This curl command is your first smoke test against the running Flask server. It sends a post request to localhost 5000/chat with a JSON body containing a system message and a user question about Python. The port is flag sets content type to application/JSON, which Flask requires to parse the body correctly. The max_tokens and temperature fields are optional but shown here explicitly so you can see how to control generation from the client side. A successful response will be a JSON object containing the assistant's reply text and the token count. If you get a connection refused error, the server isn't running. If you get a 500, check the Flask terminal for the Python tray-back. It'll tell you exactly what went wrong. Fast API is Flask's more production-capable sibling. The code here does the same job. Load model, expose/chat and /health endpoints, but adds several things that matter at scale. The chat request and chat response classes use Pydantic for automatic input validation. If a client sends malformed JSON or the wrong field types, Fast API rejects the request with a clear error message before it ever reaches your model. The /chat endpoint is defined as async, which means the server can handle other requests while waiting on I/O operations. And perhaps most practically, Fast API auto-generates interactive API documentation at /docs, which makes it trivial for anyone else to understand and test your API without reading source code. The model loads on startup the same way as Flask. Once, at initialization, install Fast API and its ASGI server with this command. UVCon is what actually serves the requests. Fast API defines the routes. UVCon runs the event loop. Both installed together here. You'll see pip resolve and install several dependencies including Starlet and Pydantic. When the command completes without errors, both packages are available. If you see a version conflict warning involving existing packages, it's usually safe to ignore for development use. But in a production environment, you'd want to pin versions in a requirements.txt. This command starts the Fast API server via UVCon. The reload flag is useful during development. It watches for file changes and restarts automatically, but remove it for production. Once running, UVCon prints the address it's listening on, typically http://127.0.0.1 8000 open http://localhost 8000/docs. That alone is worth the switch from Flask for anything you plan to share with other developers. Gradio gives you a browser-based chat interface with almost no front-end code. The setup here loads your merged model, defines a chat_fn function that takes a user message and conversation history, builds the properly formatted message list, runs inference, and returns the decoded response. Gradio's chat interface component handles the entire UI, message bubbles, conversation history, input box, and the demo.launch SSA call starts a local web server. The share equal sign true option generates a temporary public URL through Gradio's relay service, which is useful for demos or getting feedback from someone who isn't on your local network. This is the fastest path from model that works to thing I can show someone. Install Gradio with this pip command. The installation pulls in several dependencies including Fast API and UVicon if they're not already present. Once complete, you'll have access to the full Gradio component library. The install typically takes 30 to 60 seconds depending on your connection. If you see any version conflicts with existing packages, the most common fix is upgrading pip first with python man pip install bar banet pip install bar banet upgrade pip, then retrying. This command launches the Gradio chat interface. When it starts successfully, you'll see a local URL in the terminal, typically http://127.0.0.17860. Open that in any browser and you have a working chat URL. The first message may take a few seconds longer than subsequent ones due to CUDA warm-up. If you passed share equal sign true in the launch call, you'll also see a public Gradio.live URL that's valid for 72 hours, useful for quick demos without any server configuration. Monitoring and evaluation. Once your model is serving real requests, you need visibility into what's happening. The chat metrics class here tracks 4 things per request: total request count, tokens generated, response time, and error count. The log_request method updates all of these atomically. It only increments token and request counters on successful completions, keeping error counts separate. The log_feedback method captures explicit user sentiment signals, which become valuable training signal for future fine-tuning iterations. The get_stats method computes derived metrics, average response time and error rate. Formatted as a dictionary, you can expose through a /metrics endpoint or push to a monitoring system. The integration example shows where these calls go in your chat endpoint. Log before returning the response, and you have a continuous record of your model's production behavior. A /b testing lets you compare 2 model versions against real traffic rather than synthetic benchmarks. The pattern here is minimal. Load both model versions at startup, and in the ab_test_chat function, use random.choice to route each request to either v1 or v2. The critical part is the logging step. You record which version handled the request, what the input was, and what response was generated. Without that log, you have no data to analyze. After collecting enough traffic, you compare quality metrics between the 2 versions and promote whichever performs better. This is how you iterate on a deployed model without guessing. Handling edge cases. Long conversations will eventually exceed your model's context window, and when that happens without handling, you'll get either a crash or silently degraded output. The truncate_history function solves this with a straightforward strategy. Always keep system prompts intact. They define the model's behavior and must never be dropped. Then keep the most recent 10 user and assistant turns. The logic checks message count in the API handler, and if the conversation exceeds 15 messages, truncation kicks in before the request reaches the model. The threshold of 15 is a reasonable default for a 2048 token context window, but you should adjust it based on your average message length and your specific model's context limit. Content moderation is non-negotiable for any public-facing deployment. The moderate_input function here is a simple keyword filter. It lowercases the input and checks it against a list of flag terms, returning an error message if any match. In the chat handler, every user message gets checked before it touches the model. If flagged, The API returns an error response with a moderation flag in the JSON, and the model never sees the input. The keyword list shown is a minimal starting point. Expand it based on your use case and user base. For higher stakes applications, you'd layer this with a dedicated moderation model, but even this simple filter catches a meaningful fraction of misuse. Network timeouts, CUDA errors, and occasional model hiccups are facts of life in production. The generate underscore with underscore fallback function wraps your inference call in a retry loop with a configurable max underscore retries parameter, defaulting to 3 attempts. After each failed attempt, whether from an exception or a suspiciously short response that suggests something went wrong, it waits 1 second and tries again. If all retries are exhausted, it returns a graceful fallback message rather than propagating an exception to the user. This pattern costs almost nothing when things work correctly, and it meaningfully improves reliability when they don't. Users experience a slight delay instead of an error, which is almost always the right trade-off. Production deployment checklist. Before you call a deployment production ready, work through this checklist. On the model side, merge to 4-bit, verify VRAM usage stays under 8 GB, run the inference benchmark to confirm your token per second baseline, and spot check generate outputs to confirm quality held up through quantization. On the API side, implement health check and metrics endpoints, add input validation, and make sure errors return structured JSON rather than Python stack traces. For performance, verify 256 token responses complete in under 10 seconds and test what happens when multiple requests arrive simultaneously. Your server should queue them gracefully, not crash. For safety, content moderation and input length limits should both be active. Finally, confirm your logging is capturing enough detail to diagnose issues after the fact, and make sure your API is documented well enough that someone else could use it without asking you questions. Key takeaways. 6 things to carry forward from this lesson. Merged 4-bit is your deployment format. Smallest memory footprint, no adapter overhead. Fastest load time, always benchmark before optimizing. Without a baseline, you can't measure improvement. Instrument everything. Metrics are how you discover problems before users report them. Build retry logic and fallbacks in from the start. Failures in production are inevitable, and how your system handles them defines the user experience. Start with Flask, graduate to Fast API when you need validation and async, and reach for more advanced infrastructure only when you have a real scaling problem. And content moderation isn't optional. Add it before you open traffic to real users. Module 5 complete. That's Module 5 finished. You started with the fundamentals of chat model architecture and worked all the way through dataset creation, personality fine-tuning, multi-turn training, advanced techniques like function calling and retrieval augmented generation, and now production optimization and deployment. Your model isn't just trained, it's instrumented, hardened against edge cases, and running as a real API. That's a complete end-to-end fine-tuning pipeline built from scratch on consumer-grade hardware. What's next? 2 paths from here. If you want to keep building, Module 6 covers advanced techniques, things like continued pre-training, domain adaptation, and more sophisticated RLHF approaches. Or take what you built in this lesson and deploy your model right now using the scripts you just wrote. Both are valid next steps. The deployment code is ready to run. Additional resources. For deeper reading, the Fast API documentation covers everything about async endpoints, dependency injection, and production configuration. The Gradio documentation has examples for more complex UI patterns if you want to extend the chat interface. The Unsloth GitHub repository has an up-to-date model optimization guide covering quantization formats beyond what we covered here. And the Production ML Best Practices Guide from Google's ML engineering team is worth a read when you're ready to think about reliability at scale. Congratulations on completing Module 5. You've earned the title of Chart Fine-Tuning Practitioner. This chart compares 4 popular inference engines running a 7 billion parameter model across 2 dimensions: throughput in tokens per second and memory footprint in gigabytes. VLLM leads on throughput at 185 tokens per second, followed by TGI at 160, Ollama at 130, and Llama.cpp at 12. Memory tells a different story. Llama.cpp uses only 3 GB thanks to aggressive CPU side quantization, while VLLM uses 22 GB, TGI 24 GB, and Ollama 28 GB. The pattern is clear. The high throughput engines assume you have GPU memory to spare. If you're optimizing for speed and have the VRAM, VLLM is the choice. If you're deploying to edge hardware or a machine without a discrete GPU, Llama.cpp memory efficiency is worth the throughput trade-off. Your P40s with 24 GB each sit comfortably in VLLM territory. This scatter plot maps quantization formats for a 7 billion parameter model along 2 axes: relative accuracy on the vertical axis and model size on disk on the horizontal. The formats cluster in a clear pattern. BF16 and FP8 sit in the upper right, high accuracy, larger files. INT8 holds close to full accuracy at meaningfully smaller size. As you move toward Q4_K_M and Q2_K in the lower left, file sizes drop significantly, but accuracy starts to degrade. The practical takeaway: Q4_K_M is the widely accepted sweet spot for deployment. It cuts file size roughly in half compared to FP16 while keeping accuracy loss below 1% on most benchmarks. Q2_K is only worth considering when disk space or memory is genuinely the binding constraint and you can tolerate the quality hit. For your use case with 24 GB P40s, Q4 gives you the best of both. This diagram compares 2 batching strategies side by side. Static batching on the left waits until a full batch of requests is assembled before starting inference. If you have 8 slots in a batch and only 6 requests are ready, the system waits for 2 more before processing anything. That idle waiting time directly reduces GPU utilization. Continuous batching on the right fills processing slots the moment they become available. As soon as one request finishes and frees a slot, the next queued request moves in, no waiting for a full batch to assemble. The result is significantly higher GPU utilization under variable load, which translates directly to more requests served per second with the same hardware. VLLM's paged attention system implements continuous batching natively, which is a large part of why it leads on throughput benchmarks. These 2 graphs show the fundamental tension you'll navigate when tuning a production inference server. The left graph plots latency, both median P50 and tail P99, against increasing batch size. P50 latency stays relatively flat as batch size grows, meaning typical users don't feel much slowdown. But P99 climbs, your slowest requests get slower because they're waiting longer in the queue behind a large batch. The dashed SLA line at 2 seconds marks where user experience starts to degrade. The right graph shows throughput increasing with batch size, which is the upside. More requests per second means lower cost per request. The optimization problem is finding the batch size where throughput is high enough to be efficient, but P99 latency stays below your SLA threshold. There's no universal answer. Run this experiment on your own hardware and your own traffic patterns to find your specific crossover point. This ladder ranks GGUF quantization levels from Q2_K at the bottom to F16 at the top, showing file size in gigabytes alongside quality retention percentage for a 7 billion parameter model. F16 comes in around 13 GB and retains essentially 100% of the original model quality. Q8_0 cuts that to about 7 GB with negligible quality. Q4_K_M, the recommended deployment format, sits around 4 GB and retains roughly 97 to 98% quality. Q2_K drops to about 2.5 GB. The ladder makes the trade-off visible. Each step down saves meaningful disk space but costs some quality. For most chat applications, Q4_K_M is where you stop. The quality retention is high enough that users won't notice the difference, and the size reduction is substantial enough to matter for deployment costs and load times. Speculative decoding is a clever inference trick worth understanding, even if you don't implement it immediately. The idea: instead of running your large target model, say 70 billion parameters for every single token, you first run a small draft model, maybe 3 billion parameters, to quickly generate a few candidate tokens. Then the large model evaluates all of those candidates in a single forward pass, accepting the ones that match what it would have generated and rejecting the ones that don't. Because the large model processes multiple tokens per forward pass instead of one, and because the small draft model is fast, the net result is 3 to 4x faster generation compared to standard autoregressive decoding. The quality is identical to running the large model alone. You're not approximating, you're just being clever about which computations to batch together. This table gives you a quick reference for choosing an inference engine based on your deployment context. VLLM, written in Python, delivers very high throughput and is the standard choice for production API serving. It's what most teams reach for when they need to serve many users efficiently. Llama.cpp, written in C++, is the go-to for CPU inference and edge deployment, and it's what powers Llama, which wraps llama.cpp with a developer-friendly interface for local use. TGI from Hugging Face combines Rust and Python for very high throughput and integrates naturally with the Hugging Face ecosystem. Xllama v2 targets consumer GPUs specifically and achieves very high throughput on hardware like your P40S, worth evaluating if VLLM's memory requirements are a concern. Triton sits at the enterprise end, maximum throughput, maximum complexity, built for large-scale infrastructure teams. For your current setup, VLLM or Xllama v2 are the most relevant options to explore next.